organization, then we look at an example. And then, so we finish this topic, we go to the next one. So far, when we study, we only look at whether I create a sequential file, or I create an index sequential file, or I create a sequential file plus a B tree or B plus tree index, or I create a hash file. But we also can cluster multiple tables in one file. And this is they call multi-table clustering file organization. And in Oracle, it has it. Now remember, when you do the individual project, in task 3, which is the one that you have to discuss and decide the file organization for each of your tables. In task 3.1, you assume that all the data structure, all the file organization we study in class are available to you. So you discuss based on them. But in task 3.2, it requires you to read Oracle documentation to be able to understand what file organization that Oracle has and which one it does not have. And then you discuss based on that. So let's say, suppose in task 3.1 you say, I want my file to be extendable hashing based on, let's say, based on instructor name. But then when you look at Oracle, then you say, suppose Oracle doesn't have that. Then you have to find out among the Oracle's supporting file structure or file organizations, which one would be the best among them that you can choose. And then you have to provide your justification. Okay? So nowadays, you have to be able to learn a little bit, read a little bit from Oracle websites. They have very good documentation. Read it to understand it. So the multiple table clustering file organization is when our queries require multiple tables. And those queries occur very often. Okay? So we may want to put multiple tables in one file instead of in separate files. So for example here, I have a department table, I have instructor table, and let's say now I want to put the two tables together. So look at here, these two tables cluster based on the department name. So look at computer science, Taylor, and 100,000. That's the information from department. Then after that, we cluster on the instructor that work for computer science together. So these people here, those are 3 people that work for computer science. You see like the first row there, the third row, and the fourth row, all of them work for computer science. So we will store them right after this one. Okay? Then after that, we store the second tuple of department, which is physics. Then after that, we store all the instructors that work for physics, right underneath that. So that is what we call clustering these two tables. And the cluster key, which is the one that we use to put them together, is based on the department name. Because both of them has a department name in there. Okay? So this is we call the cluster of multiple table clustering file organization. Now, so when is it good? What kind of query would be good to do this? If your query involves the choice of department and instructor. Remember when we do the choice, we have to do Cartesian product. We will need those two tables together, right? So instead of going out and bring the instructor alone and then going out and bring the department alone, if our choice query, just like you say, select something from department, instructor, where the department name equal to instructor department name. Okay? Just like you have a join query in SQL like that. Then and if the query occurs a lot, then you want to be able to put both these tables together in the same file. So that when you perform this query, the system only needs to go out and bring this file, instead of going to bring in two different files. Okay? So that is the first thing. So it's good for the query that involving department join with instructor. And also for the query that involve only the department and its instructor. Okay? Just a single department. However, what happens if the query only involve department alone? Let's say I just have a query like this: select department name from department. I only want the departments, I don't want the instructor. If I store department separately, then the system will go and just bring the department in and work on it, right? But since I put together in the same file, then you have to bring in a big file in order to be able just to retrieve the department alone. So it has the trade-off. Do you get what I'm trying to say? Think about you have this query. Let's think about SQL. Okay? Let's say you write this query. Select, let's say, department name or whatever here. And maybe building or budget or whatever there. Okay? From department instructor, where department name, department name equal to instructor department name. Okay? So what is this query? So suppose we have this table. We have this one here. Let me make it more interesting. I want to join the two tables. So I want to join these two tables. This is a join operation, right? And I join by joining through the department name. Okay? This is really a join operation, so don't look at me like you haven't heard of it. Okay? We already took a midterm. So this is a join query in SQL. It joins these two tables, and the join key in this case is this one. So if I have these two tables stored separately, then the system has to go out and bring in this table into main memory. Yes? It makes some I/O to bring this in, and then it makes some I/O to bring this in. And then it performs the Cartesian product. Then it compares this condition. Then it pulls out the result. So very expensive process. But if this query occurs a lot of time in my application, then I may want to cluster these two tables together, meaning put them in the same file. So if I put them in the same file like this, then when I perform this query, it only needs to bring in this file, yes? And then what does it do? Remember, you want to retrieve the one that has the same department name, yes? Everybody down here is the same department name. So by looking at this, it can tell all of these people have the same department name. It doesn't need to compare anything. It's right here. And everybody down here, it has the same department physics, yes? So it doesn't have to perform Cartesian product like normally we would have to perform. So you'll be able to reduce I/O plus reduce the memory access time when you perform Cartesian product. Because here everything already here. All of the instructor is the same working for computer science. All the instructor here work for physics. So we don't need to do Cartesian product and then pull out those tuples that are the same department name in both. So very fast. So we don't do this if this query, if this choice query occurs a lot in our application. And that's what this trying to tell you here. This one. This is the joint operation when we study relational algebra, which is the next topic. You will see this notation. Yes.
And the SQL code for that doesn't have to change if it's stored in that way. It's still the exact same way.
It does not.
Okay.
That's the nice thing about, remember we're talking about physical independence. That's the major advantage of having a DBMS. You write your application, meaning you write your query, yes? Your query don't have to change, even though you change the physical structure of the data. You change it from whatever table you had before, now you put them. The logical is still there, right? The logical in your metadata is still two separate tables. But physically, you put them in the same table. Now, but here we say back for queries involve only department. Let's say I write, so this is the joint query, right? Okay, now if I only have this query, select, let's say, budget, okay, from department. I only want the budgets of the department. I don't want any other relation. I just want this relation. If I had this table separately, if I had this file separately, then very simple. It can go in here and bring this in and retrieve this column. Yes? Very simple. But if I have even faster, if I have an index on budget, yes, then it can even go in and retrieve it quickly too. But it doesn't matter what, they only deal with one table. But now, since I put the two tables together, so when I run this query, even this query only view one table. Physically, we don't have two tables. Logically, we have two tables, but physically on the file, we only have one table, which is this one file. So it has to go in here, bring this in. Bring this in, and it has to go to this column, this row, retrieve this, and then it has to skip all of these and go here and retrieve this. Right? Because the query only asks for department, it doesn't ask for instructor. So it will take longer to process compared with if I just had this table alone. So one way people trying to solve this is they add the pointer. They add the pointer, they chain these together. So if you only retrieve department information, then it go here and it follow this pointer to go here. Okay? So that depends on how the many queries you have in your database and what query is occur more often than the other. That's why in the individual project, if you look at the set of queries I give you, I also give you the frequency associated with each query. So I say this query occurs, let's say 5 times per month or 10 times per year, whatever. So that is the frequency. And then in here, it talks about also, and we looked at this before, how to create index. And also you also can drop an index. Let's say you create an index and then after some time you decided that your query changed, you don't need that index anymore. Let's say before you have a query, let's say select department name from department where budget between 10,000 to 500,000. So you have a range query. You say, oh, so that would be good if I create, let's say a B+3 index for that on budget. But then later, let's say that query occurs very seldom or it does not exist anymore in your application. Then you may not need that index anymore. Then you can drop the index. Okay? Let me ask you this, why should I drop an index? Why don't I just leave it there? I know that I don't need it anymore, so why don't I just leave it there? Why don't I bother to drop it? Is there any overhead of having it staying around in the system? Remember, when you insert data into the table, the DBMS have to deal with the index for the table. So it will have to insert that, whatever value you insert into that index, even though you don't need that index anymore. That's why it still have overhead even though you don't use that index. But it actually indirectly used when you insert data. So that's why if you know that you don't need that index, you don't have the query that will be improved by having that index anymore, then you just drop the index. So here are the factors when you decide on a file organization for a table. Okay? You need to think about the types of queries you have on the table. That's why in your individual project, because you have to decide the file organization for each of your tables. After you design the ER diagram, you convert it into the set of tables. Then now for each table, you look at your query to see which one is using this table. Which one, meaning which query is using this table, and what is the frequency of those queries, and what kind of query is it? Is it a random search? Is it a rand search, or is it insertion, or is it deletion? All of these impact your decision on the file organization. For example, we already studied that hashing will not improve rand search, because when you use a hash function, it can insert anywhere in any bucket. It doesn't have an order. So hashing table should not be used when you have a lot of rand search for that particular search key on that table. So let's say if I search, I say finding out the department name from department where the budget between 10,000 to 100,000. So my search key is a budget, yes? But if I create a hash, doesn't matter static hashing or extendable hashing. If I create a hash based on a hash key, not on budget, but let's say on department name, does it have my query? My query is searching based on budget, yes? And I say, okay, now I'm going to have a hash. I will create this table as a hash table based on budget. Will that hash table help me improve my query, looking for departments whose budget between 10,000 to 500,000? No. In the hash, you cannot have an order. You don't have an order. You don't know where is it after 10,000 will be 11,000, will be 12,000 or what. Maybe 10,000 go to bucket 1, but then 20,000 go to bucket 0. And then 30,000 go to bucket 100. It can be anywhere based on your hash function. So that's why it does not have rand search whatsoever. So you don't create a table as a hash table, hash file because of the rand search. But if many of your queries are random search, so let's say you say select department name from department where budget equal to 10,000. One specific value, right? So if you use it as an index, then you have to travel the index to find where it is. But if you use it as a hash, then you apply the hash function. In the best case, you apply the hash function on 10,000, it will give you the direct bucket address. And you can go there and retrieve your record, right? In the best case. In not too bad case, you may have to go to some overflow bucket. Okay? But in general, it's good for random search, right? And insertion, if you use static hashing and you put a bunch of insertion, very soon you will run out of space. So you want to use extendable hashing. But we know that with B plus 3, it's good for both. It's good for rand search, It's also good for random sort. It's not as good as hashing, but it's also good despite of insertion and deletion. That's why many commercial database systems use some kind of B family tree structure for index by default, but not the hash one. Okay? And then we have to know the frequency of queries, how often this query occurs. We have to know the access time for this particular machine. We have to know how much time it takes for insertion, deletion, and space overhead. So all of those factors need to be taken into consideration. So let's look at this example. Okay, here's the example. I will give you the following tables and the queries, and I want you to find out. So you need to pay attention to this. This is small example, but if you understand this example, then it shouldn't be difficult for you to answer the question 311 for your individual project. Okay, let's say I have this table here.
但是我们就是Google Project，因为大家都会帮忙。
Let's say I have student, and student has a key, social security number, have name and address. Then I have another table called course, and let's say course number is a key, and then I have course name, and then faculty. And then I have enrolled, social security number and course number. Together is a key. So this tells which student enrolled in which course. Then I have one more table on department. And department have department name to be the key. And then it has budget. Okay? Very simple. I got totally 4 tables. Then I have the following queries. So 4 tables, and let's say I have 5 queries. So this is query number 1. Query number 1 say insert a new student and associate him or her with a course. Okay? And I also give you the frequency of this query. Let's say I say this occurs 50 times per day. Then I have the second query. Say insert a new course. And let's say this occurs 100 times per month. Then query number 3 say 5 on students who take course number 1, 2, 3. And suppose this occurs 10 times per day. Query number 4 say insert a department.
我看不懂他写的字。
And let's say it occurs only once a year. And the last query say find on departments. Whose annual budget is between, let's say, 1 million to 10 million. And let's say this occur maybe 6 times per month. Okay? Well, let's say just 1 time per month. This doesn't occur much. 1 time per month. All right. And your job is to find out what is the most appropriate file organization for student, for course, for enroll, and for department. Considering all the file organization that we have studied in class. This is very much the same as your question 3.1 in the individual project. So this is how you do it, okay? And I would like you to answer this way when you work on your individual project, very systematically. Don't just, I have seen some students answer like a paragraph and paragraph, but it doesn't tell me anything. I wanted to go to the point, okay? I want to see the meat. I don't want just a bunch of words. So here's how you do this. Your answer is the following. You do in this format, and if you do this format, then you're more in control of it because everything is very systematic. First of all, you write down the table name because you have to make decision for each table separately. Then the next column will be type of query. Then the next column will be the search key in that query. Then the next one will be frequency of that query. And the final column, which is your answer, which is the file organization. The one that you really have to answer, okay? Like that. So now, let's work on one table at a time. You have 4 tables. You have to give 4 answers here. So let's look at the first table, student. Okay, student. Let's look at to see what query is accessing this table. Because the file organization, like I said, is impacted by the queries that using the table, that access the table. The queries that don't access the table at all, it has no impact on this table. So out of the 5 queries we have to find out which one will access this table, directly or indirectly. We may be able to see very clearly from the query, and some we may not see clearly, but it is behind the scene. So, which query out of 5 queries we have? Which one that use this table?
Only number 1.
Number 1, okay, so let's write down number 1 here. Okay? And what type of query is this? Insert. And what search key? It doesn't matter because it's insertion, not searching. So we don't have to care about this. What is the frequency of this query? 50 per day. Huh? Is that all?
No.
Some of you say yes.
No.
Is there any of you say no?
Third one.
Okay. How about query 2? Does it impact this table? No. How about query 3?
Yes.
Yes.
How does it impact this query? Like this table. It says find all students who take course number 1, 2, 3. So you are given the course number 1, 2, 3. Yes? Where do you go? to answer this query?
Enroll.
You go to enroll, yes? From the enroll, you find out the social security number, yes? Then what do you do with that social security number?
Search.
You use that social security number to go to the table student, yes? To search for the student name, because we want to find all students, yes? So when you search this table student, what kind of search is that? Is it random search or random search?
Random search.
Random search. You are not given the social security number directly from the query, but indirectly, yes? And so after you put in 1, 2, 3 as a course number, you find the corresponding social security number. Then you use that to search. That is a random search based on that specific social security number. So we say that yes, we do need query 3. Okay? And this is, what type of query is it? We say random search. And on what search key? Social security number. Okay? So social security number. And we do the query 3, we do the 10 per day. Is there any other query using this table? How about query 4? No. How about query 5? No. Right? So in this database, for this table, the only 2 queries that really need the data from this table. Okay? So we got 1 here. So now we can make the decision now. We have 10 per day, right? It's a lot of insertion. And we do, 50 per day is a lot of insertion. And we do random search. So what kind of file organization should be good? We say, okay, random search, so we gotta be hashing. In your mind, you say hashing. Hashing based on what? What is a hash key? The hash key gotta be the same like the search key, yes? Now, when you see you have a lot of insertion, should I use static hashing? No. Static hashing is not good when you have a lot of insertion deletion. We talked about that before because we need, for static hashing, I need to know the number of buckets in advance. So I need to know, okay, I need 100 buckets. But if I have many insertion over time, I will run out of it. Then I have to redo my hashing again. So it's not good if I use static hashing. But luckily that what other hashing we have studied? Extendable hashing, right? So we can use, we say dynamic or extendable hashing, the same thing. Dynamic hashing or extendable hashing with hash key social security number. That's the complete answer. Okay? So we finish this table. Now we go to second table. So let's say enroll. So what queries do we need for enroll? What query?
Sure.
Only 3?
2.
Okay, we know that we need 3, right? We know for sure we need 3 because we gotta use course number 1, 2, 3 and search this table to find the social security number, right? And so that is random search, right? Random search based on what? Random search based on what? How do you search this table for query 3? You put in the number 1, 2, 3 and you search. Yes? You search to find the corresponding social security number. Yes? But what you are given here is 1, 2, 3, which is course number. So your search key will be what? So this is random search. And your search key is course number. And that query 3, so I do the 10 per day. Is there any other queries? I need this table. Okay, look at number 1. Number 1 is say insert a new student and associate him or her with a course. After I insert a student, so I insert the social security number into the student table, yes? Then I gotta go to the enroll to insert him in order to associate him with a course. So I actually insert into this table, yes? Not just insert in the query number 1, not just insert in table student, but actually also have to insert in the table enroll. So that is insertion from query 1. And insertion, we don't have search key to insert. PP per day. Okay, so what kind of file organization we should have? We have a lot of insertion and we have random sort. With course number. Okay? So we have dynamic or extendable hashing, the same thing in our case, with hash key course number. You see, if you just say dynamic hashing or just extendable hashing, it's incomplete answer. Because you see how different between the two? That's why the hash key very important. Alright, so we finished another table. Now let's go to the table course. Okay, course. What query is this?
Number 2 is insert.
Okay, query number 2, insert.
And this is like roughly 3 a day.
And that is 100 times per month. It's still a lot, 100 times per month. Is this? Did I did correctly? Yeah. Okay. So what kind of, here's the thing, this is a tricky part. Let's assume that I don't have foreign key. Okay? So let's assume that I don't have the foreign key course number that referencing the defined in the enrollment, that referencing course. Because if we define on the integer constraint, then when we define the table enroll, we will have to have a course number as a foreign key that reference the course number in course, yes? But remember, integer constraint is up to us. DBMS doesn't require that. If you put integer constraint, then DBMS will check for that automatically for you. But if you don't put in there, it will not complain, it just doesn't check for you. So let's assume that we don't have foreign key. We don't declare course number to be a foreign key in the table enroll. Okay? So therefore, the only queries that use this table course is that query, which is the query number 2. Okay? So what kind of file organization we should have? Who remember this? A heap file. When on you got the insertion, you don't have anything else, any other queries on this. You don't know how it will be used in the future. All we know right now, you have to take care of insertion. And you want to take care of it fast. So the heap file will give you the fastest insertion. Okay? So this table will have a heap. And a heap, you don't have to say what search create anything. You just add one couple after another. Okay, now, this is if. Right now is, let's say, if no foreign key, course number, referencing, in the enroll table, referencing course table. Okay, then that is correct. Now, but if this assumption is not true, let's say when you define the table enroll, you declare that the course number in the enroll is a foreign key, referencing the table course. So that means every time you insert something into the table enroll, the DBMS has to check to see whether that course number already exists in the table course or not. Yes? Are you clear? Because you want the DBMS to do that. That's why you declare it to be foreign key. So automatically there's a search going on every time you do insertion. When you insert in your query number, number 1, right? When you insert a student and associate him or her with a course, meaning you want to insert into the table enroll, yes? And when you want to insert that, because the DBMS check the tables are all, this table has a foreign key, but reference course. So DBMS will check to see whether that course number that you want to insert in enroll already exists in the table course or not. So it has to search that table for that course number. Okay? What kind of search is that? It's random. Let's say you insert a student and you want to insert him into the course CS 4513, right? So the system has to check to see where the CS 4513 already exists in the table course. So it search for that. So that's a random search. So the random search based on the course number. So here we say otherwise meaning if this assumption is not true. Okay? If this assumption is not true, meaning if there is a foreign key based on course number, then in that case, our answer is not just this, but our answer will be what? Beside this, it will be what? What query we need? Query 1. Beside this, we also have query 1, random search. Okay? And the random search here is based on the course number. And query 1 occurs 50 per day. So then in that case, it's not just a heap file. The heap files are only good if you only inherited insertion, nothing else. But in our case, besides insertion, we also have random search. So we couldn't use the heap file, right? So meaning that this is not correct. If this is true, what should it be? It could be extendable or dynamic hashing with the keys or with the hash key course number. Because we have a lot of insertion and a lot of random search. Okay. So if it is true, then you got that result. Otherwise, then you got this result. Only one of them. You cannot have two organization for the same file. Okay? Okay, now we go to the last one, table department. Any question on this one so far? So let's go to the last one.
I have a question.
Yes.
Could we maybe also argue that you could use static hashing here because the inserts are so much less frequent than the searches?
Well, insertion 100 times per month, that's a lot, right? Unless if you say, it's not about comparing that with this, but overall. So if it may occur maybe once a year, then you can say, oh, we don't need to extend our buckets a lot. But 100 per month, that's a lot. So it's not about comparing that number with this number, but look at the overall, how it would impact our whole database. Okay, now let's go to the last one, which is the table department. Okay. So here's the department. Okay, so which query you think would impact department? This is a list of queries here. Does this first query impact department?
No.
No. Does this query impact department? No. Does this query impact department? No. This query, right? Insert the department. So we have query number 4, insert, and that occurs, let's say, once a year. What else? Okay.
Well, we don't know what the salary budget is private is a huge and so I think that actually is not accurate range.
Why it's not a range? It's a range based on the budget. Right? Remember when you design the file structure with the search key not necessarily the primary key. It can be any attribute or the set of attributes. So in this case, I want to find all departments who budget is between 1 million to 10 million. If we don't do anything with this table, then we have to search everyone. Yes. So, but in this case, we have a range. Would hash good for this? Should I organize this table to be a hash table? But before we worry about that, we need to write it down here. We need to type this query, thus we need query number 5. And query number 5 is a ransom based on the budget. And query number 5 occurs once a month. Okay? All right, so what file structure should we do this? Should I use B plus 3? What are the file organization that, because we don't do a lot of insertion here. You see that once a year is very seldom. The thing about the B or 3 or B plus 3, you do so many insertions, you have to modify the tree. You have to rebalance the tree, so it's that expensive. But in our case here, we don't do a whole lot of insertion, just once a year. We do actually more search than even insertion, right?
Index sequential file. Using index sequential file with imparse.
So you could use, remember we studied sequential file, then we studied index sequential file, then we studied sequential file with the index as a B3 or B plus 3 before we studied hashing, right? So I could choose the scene, it doesn't have a lot of insertion. with index sequential file, the bad thing is if you have a lot of insertion and you a lot of time, you may have to reorganize your sequential file. But in this case, your insertion is so seldom. Okay? Then you could use the index sequential file. So I could have an index sequential file
족보는 고등어.
with what search key?
일단 고등어. 작게.
What search key that I will use to organize this?
Budget.
저건
So the budget.
제가 好久没更新。但是固定了说。
So that's very much the example. Simple example, but it has really very much everything that you could think of based on our data structure that we have studied. And so I would like you to really answer question 3 in this format. Assuming all the data structure we have studied available to you, and you answer 3.1 this way. And now, suppose let's say after you already decide this, so you have this answer. And now let's say you say, okay, I look at the documentation of Oracle, and let's say Oracle doesn't have it. I'm not going to tell you what Oracle has. You really need to do some reading. Nowadays, when you go to work, no company expects you have learned everything in any university. But they expect you to be able to find the material to learn. Instead of waiting for people to give you the material. Now it's so easy, right? Most of the things on the internet. So you have to learn how to read Oracle documentation and figure this out. Okay? So suppose you find out, oh, this is, no, Oracle doesn't allow this. Then you find out what is the nearest one that Oracle allows. Let's say suppose Oracle allow heap file, Oracle allow, let's say, hash file, and Oracle for sure have a B family tree index. So among those three, which one would be the second best for you? It would be B tree structure, right? B family kind of index. Because it's still an index. So it still facilitates range search. But if you hash, then it doesn't facilitate range search. If you heap, then it doesn't facilitate any query except insertion. So you find what is the nearest result that you can have. Okay? Then you justify that and give your solution. This kind of exercise really distinguishes you from students taking this course in many other universities. A lot of times they tell you to do ER diagram, to write SQL, but not really coming to this level. But this really you feel like you're in control of determining how good is your query should be. Okay? The last thing we have in this topic, and then we go to the next one, next topic, is and this is just a quick review, a quick description here. So we have studied the database, but as I said, inside the database you have metadata. You have a data dictionary. That's where the system stores about the structure of your file, the definition of your tables, what attribute you have in, okay, what attribute you have in each tables and so on. So it's stored in the data dictionary. So if someone asks you what is the data dictionary, at least you need to be able to mention some kind of information. So for example, it stores information about the relation. It's stored in there. Okay? And actually in Oracle, you can retrieve it. You can look at what you have in the metadata. It has a command for you to look at it. Okay? So what the name of the relation you have, what is the data type and the size and so on, the attributes you have in each relation, and later when we study security, when we go to the topic on privacy and security, we will study about bills. So view is another type of like a virtual type of relation. It's not real relation. It's a virtual relationship based on the results of some query. So you can create a view. So let's say the table has department name and have department budget and then the building. But let's say you say, I don't want to look at all of those three. Most of the time, I just want to look at department name and the building. Then you can create a virtual relation that only have department name and building. And that we call view. Okay? And the interaction strength like primary key, foreign keys, and so on. And some user and accounting information like what is the password, what is the user ID, and even including the access control. And later when we study privacy security, we study that. Let's say the DBA only give you the access on certain table, on certain columns, and that will be in there, or you can define that so that other people only can look at, let's say, the building of the department, but cannot look at the budget of the department. So you can define the information about access control, which is security for your table. And then some statistical information, like how many tuples you have in each relation, and this information about statistics. So the DBMS gather this periodically. So this information changes over time. And later when we study query processing, you see that the DBMS use this information to optimize your query. And that's why the optimization is only based on the estimation, because the number of tuples you have is never exact, because it doesn't collect all the time, otherwise too much overhead. So it may collect that information, let's say every hour or every day. So when you change, right at the time you change, it doesn't know that, right? And also the physical file organization, as a hash file or index, where you have an index stored in there, and so on. Okay? So all of those are in the data dictionary. And if you look at it, it looks like this one. This is the schema diagram, but this is for the data dictionary. So you have like a table that stores the metadata for relation. Each relation is for this information. Then for this one, it also associates with it the table that stores the attributes information for that relation, and so on. And here the index, and here the view, and here the value user information. So this is like a schema diagram for your data dictionary. Any question here? So that is the end of this topic. So now we will, if you have no question, we'll go to topic number 5.
真清一些悠悠。你刚才说了刚才？你刚才说了？刚才那个玩意儿输了。再开一把。换个头。我想的。APP 自动关闭。可以这么做。绿色的。那天吃鸡我打到第5名，吃鸡，第5名，垃圾。你觉得像我玩战地那个水平
？Okay, so we have studied SQL. SQL is an implemented language of a DBMS, but it's not really a formal language. Okay, it's just people implement it. But before that, there is something we call formal relational query languages. This is really the foundation of query language. So in this topic, we will study several things. We study relational algebra, then we study tuple relational calculus, and we study domain relational calculus. So you see that most of your SQL really based on relational algebra. Some of them is based on tuple relational calculus. So let's see what is the, when we talk about database query languages, there are two types of languages. One is we call procedure language and one is non-procedure language. Have you heard of this before? What do you think procedure language is?
procedure language. PLSQL.
Like C is a procedure language. Okay? So in the procedure language, it has a procedure. So we as a user, when we write this language, when we write a query in this language, we will specify the operation. We specify the step by step how things have to be done. Okay? So when we say the user here means the one who writes the queries in this language. The user specifies a sequence of operation. To obtain the desired information. This is, we studied 3 kinds of formal languages. This is relational algebra. So in relational algebra, we will specify the sequence of operations. Let's say first we want to join and then we want to select. After is the set of operations. Then with non-procedure languages, the user does not specify a sequence of operations. It does not say what operation you have to perform. But the user specifies only the desired information without specifying the operation or specify how to get it. So we only tell the system, this is what I want. That's it. It doesn't say what operation you should perform.
Is that supposed to say without instead of with?
Hmm?
Is that supposed to say without instead of with?
Oh, without. Yeah, thank you. Without specify how to obtain it. Well, so some of you do pay attention. Thank you very much. Okay. This one here is a tuple relational calculus. And also domain relational calculus. So you may say, well, just tell the system what I want. It got to be easier than tell the system how to get it, right? But actually later you will see that somehow our mind trained to work in procedural way. So easy for us to tell the system, okay, do this, do this, do this, than just express what we want. And because when we want to express what we want, it's not like you just express in a natural language. But you have to follow the syntax of these languages. So there are 2 languages that belong to this one is tuple and domain calculus. So in here, the first thing we study is relational algebra. You will see that it's very closely related to SQL. SQL is built on top of it. So it's a procedure language, and it really only has 6 basic operations. It has a select statement. In SQL, we say select, but in this language, it's this kind of operator. This means select. Then this means project. Now, in SQL, you just say select. It doesn't matter. You select the whole tuple, so you just select one attribute. But in this language, if you select the whole tuple, then you use this notation. If you just select some attributes, then you use this notation. And this we call project. Then you can have union. Union two sets, just like you do in SQL. You can do the different, set different. Okay? You can have Cartesian product. Now, in SQL, when you say select something from department instructor, where department name equal to instructor department name, right? Automatically, the system sees 2 tables. Automatically, it performs the Cartesian product behind the scene. As far as you're concerned, you only see a simple SQL statement, but there's a Cartesian product. So in relational algebra, we have to specify what operation we want the system to perform. So we cannot just leave it the system to decide what to do. So like in this case, if we wanted to perform Cartesian product, then we use this notation. And sometimes, just like in SQL, sometimes we want to compare the tuple in the same query with another tuple in the same query, in the same table. So we have to rename. Remember, we have done that. We rename a table with another name, temporary, just for the query purpose. So in relational algebra, if we want to rename, we have to say you want to rename. So you use this notation. Okay? So these are the operators that for relational algebra. And here's the key thing that you need to remember. Every operator here, the input to this operator, some you take 2 relations as an input. Some only take 1 relation as an input. But the input gotta be a relation. So here, if you want to apply select, then your input gotta be 1 table, 1 relation. Okay? If you want to do union, then you need 2 relations, and so on. And what is the result? The result of a relational algebra query is a relation. It might be just 1 tuple in it, but it's still a relation. So it takes in the input as a set, 1 set or 2 sets, and the result will be another set. So here, let's look at the relational algebra, the query processing flow, so that you can see the relationship between SQL and relational algebra. So here your SQL query. Okay? You write in the SQL query, because we want to show the flow here. How does the query process in the DBMS system? So when you submit the query, you sit in front of Oracle, you submit this query into Oracle. This query go into Oracle and it go to the component inside the Oracle called query parser and translator. That is a part of the query processor component inside Oracle. Now, have you studied parser before? Which course you learned that? And also in compiler too, right? You type it in a programming language, let's say C or whatever, for every statement in there gotta be parsed. So meaning it check against the syntax, let's say C, it check against the syntax of C. Then it have to pass that segment according to the C grammar so that it can execute it later, right? But first it has to do that. So same thing here. So it has to pass based on this language, right? It is SQL language. Then here's the interesting thing. Up to this point, still just SQL. Then now, it will convert it, it will translate it into a relational algebra query. You don't see it, but that's behind the scene. That's why as a computer science student who take database course, you gotta learn the formal languages. You cannot just simply learn SQL, like students from business school and so on. So this is the foundation here. Even without in this form, but inside Oracle or DB2 or MySQL or SQL Server on the DBMS, it will be converted into this format. And so we will learn the format of this, okay, this language. After it goes through this, then now it will supply that to a component within the DBMS called Query Optimizer. So the Query Optimizer doesn't take SQL as an input, it takes the equivalent relational algebra query as an input. And remember, we also store in the data dictionary zone, we also store statistics about this database. So we have, and this information may be on this, or maybe in my memory, whatever. So it has statistical data, which is like the number of tuples we have in this table, and the number of distinct values of the attributes in this table, and so on. So it takes the information from here. So this component inside Oracle, it will take this input as a relational algebra query we have, plus the statistical information we have inside the database, in order to optimize this query. Remember, it doesn't optimize the SQL query directly, it optimizes this one. And later when we study query processing, you will see how it optimizes. Okay? After it optimizes, then it will produce an execution plan. How to execute this query. And even you may write very inefficient SQL query. Therefore, you have very inefficient relational algebra query. But through the optimization, it be able to convert this into a more efficient relational algebra query. It's equivalent but more efficient. Equivalent in terms of the result, but more efficient in terms of time. Then after that, this one will pass through another component within DBMS called Query Execution Engine. Okay? And this one may need some data from the database. And then when it finishes, it gives you the query result. So that is how the process looks like. And what I want to show you today, before we leave, is this part right here. You see how important the relational algebra query in the process. Without this, there's no DBMS. Okay? All right, let me stop here, and next time we continue with this topic. And this topic for sure will be on your final exam.
强哥，不是那个。